Hello everyone. So today we are going to discuss how to model a channel for single source, which will include both line of sight as well as non-line of sight component. So for this we will do for indoor system. So suppose this is your indoor. You have one transmitter here and receiver here, and we want to model the channel, optical wireless channel here. So suppose the PE is the power emitted by the source. And PR is the receipt power at the receiver. And this is the optical wireless channel transfer function. Actually, this should be written as NLoS. The 0 actually stands for DC. This is for DC, assuming this is a DC channel gain. And then HLOS can be defined in terms of channel impulse response in this fashion. So now let us try to understand how do we model that optical wireless transfer function. So suppose this is your LED. This is the receiver plane, and your receiver is, say, somewhere here. And this LED can have a radiation pattern depending upon the value of Lambertian parameter M. It can be a narrow emission, it can be a broad emission. Let us consider LED, which is a broad emission, and assume that this is the and this is the normal. This is not coming clearly here. So this is the emission pattern, and this is the normal, and then this is the receiver, and it has some FOV, and this is, say, the normal here. Now, the ray from source falls onto this receiver and is collected by the receiver because it is falling within the cone of the receiver FOV. So this angle, let us say, is phi, and this angle, which the emission pattern makes with the normal, is actually half irradiance angle, which we had discussed in the last class. So let us denote this by half irradiance angle. And this angle at the receiver, the ray makes with the normal, let us denote this as theta. And the total FOV is this angle normal with this side is, say, theta c. If the ray falls beyond this, it will not add to the receiver and you will not get any output. So with this understanding, let us try to understand this, the optical wireless transfer function. So this is given by M plus 1. M is the Lambertian parameter. A, this is area of the photodiode. This is area of the photodiode of the PD. 2 pi d square, and this distance between the source and the receiver is d. This distance is d. Cos m phi, this is the radiation pattern. This term is coming because of the radiation pattern, and m, as I mentioned, is a Lambert parameter. And Ts theta is optical filter gain if you are using some optical filter. So this will have some gain. So this is represented as Ts theta. And this is the concentrator gain, because at the receiver, you want to have a wide receiver so that you get light from all possible directions. But once you have a large photodetector area, it will have more capacitance and it might limit the data rate. So in order to take care of this issue, one uses some sort of concentrator near the receiver, and that concentrator may have some gain, so which is G theta. So this is concentrator gain. And then cos theta. This is the angle the ray makes with the normal of the photodiode. So this will have some value when as long as theta is between 0 and theta c. And this will be 0 when it is greater than theta c. So this is true for both sides. So theta c have shown here as a half FOV. Otherwise, the total FOV is 2 theta c. So this is the optical wireless transfer function. And G theta, this concentrator gain, is actually given by n squared divided by sine square theta c. And this theta should vary between theta 0 and theta c. So this is sine square theta. And it is 0 when theta is greater than theta c. And n is the refractive index of the concentrator. This is the refractive index of the concentrator. And normally when we do analysis, sometimes you take Ts and G theta as 1 so that calculation becomes a little simpler. But here I have represented Ts theta and G theta in the expression. So now let us try to, so this was the case. This was the case when you had only line of sight. So this is line of sight. But there will be components from non-line of sight. The ray or the light getting reflected from the walls or from the ceiling or from the receiver plane, and then it can be collected by the receiver. So those are referred as non-line of sight components. So let us try to find out the optical wireless channel transfer function when you consider non-line of sight. So in order to understand this, let us draw a diagram where we will consider one non-line of sight component and then try to understand this expression. So let me draw again a room where I'll show both line of sight as well as non-line of sight. So say this is say a room, and then you have a source here. Right now let us assume there is only one source because we are trying to model the channel for single source and single receiver. And let us denote this as Ti. There can be many sources, but right now I'm assuming only one source, Ti. And then you have a receiver here, which I call as Rj. This Ti will have some emission pattern or radiation pattern. and let us see, this is the normal. And similarly, receiver J will have a cone which will accept the light. So this is the cone, and let us say this is the normal. Now let us try to identify the, so this is, let us draw for the first line of sight as we had known earlier. So this is line of sight, and let this distance between the source Ti and the receiver Rj is Dij. And this angle which it makes with the normal is phi ij. And as usual, this is the irradiance angle, which is say phi half irradiance angle. So this is referred as phi half. And this angle, the maximum angle where the light is accepted by the receiver is theta c. And this angle which LOS makes with the normal, this particular angle, this is phi ij. Sorry, this is theta ij. This is theta ij. So this is for the line of sight. Now also we need to consider non-line of sight component. So let us consider just one line of non-line of sight component. For example, ray which is coming from the radiation pattern of the source strikes the surface or the wall with some area, say D wall, DA wall, or here I have used as DA capital wall, so let me write capital A. And it will have some reflection coefficient, say rho. This is the direction. And if I draw a perpendicular here, this angle is given by alpha and this angle is given by beta. And the angle which the reflected non-line of sight from the wall makes with the normal, meaning this particular angle, this angle is, let us represent this by as psi. And this distance from transmitter to this point on the wall is say D1, and this distance is D2. So the component, the DH reflected, this I am referring this as reflected from the walls. That optical wireless function, I have written D here because a small area wall is considered here. Normally, when you do the recursive method for channel modeling, you divide the whole wall into grids. So each grid actually represents one small area, differential area. So this is given by M+1. M is Lambertian parameter, area for the diode, and rho is the reflection coefficient of the wall. And then DA wall is the area, particular area on the wall. And then cos M phi, this comes from the radiation pattern of the source. And then cos alpha, this angle alpha, which it makes it the normal. And then cos beta, this angle, into, as usual, our Ts psi, which is filter gain, optical filter gain, and G psi. So let me write this, optical filter gain. And G psi is concentrator gain, because I'm using concentrator at the receiver, so that the response of the photodiode is not limited. Concentrator gain. And cos psi, this psi angle, which is the reflected ray mixed with the normal at the photodiode, and divided by 2 pi, these two distances. Earlier it was d square when I was considering line of sight. Now there are two distances involved, so this will become 2 pi d1 square d2 square. And this angle, this is valid when you have when the reflected ray is falling between 0 and psi c, or this should be theta c, because theta c is the maximum angle, and this is theta c. So this is how you represent the contribution from the non-line of sight component. So if I try to calculate the receipt power because of both non-line of sight and line of sight, this is given by PE, emitted radiation power, and this is the DC optical wireless transfer function, HLOS, plus this DHRAF into PE integrated over all the surfaces wherever the reflection is taking place. So this includes all the walls. So PE, DHRF at DC. So why I am assuming DC here every time? Because if you see the channel bandwidth, is typically of the order of 100 megahertz, which you can calculate for a room which is 5 cross 5 cross 3. 5 is the length, and this is the length, this is the breadth of the room, this is the height of the room. So the maximum path difference which it can have is, the one between the line of sight and the other path which is covered by the non-line of sight. So the maximum would be, say, 3 meters for such a small room. And if you see, the delay will be of the order of very less, few nanoseconds. Right. So basically, if you try to back calculate, it will give you a bandwidth of about 100 megahertz. Whereas the devices which are used here, the receiver and transmitter, they generally have about 20 megahertz. A good device will have, response something like this, the LED, the normal LED which are normally used in the room for illumination. So basically, it sees a flat channel. It is not a frequency selective channel. So that is why, DC gain is sufficient to represent the optical wireless transfer function. And if I calculate the SNR, which I required for calculating the BER, SNR electrical will be given by this HDC is actually combination of both the parts here, the reflected optical wireless transfer function as well as the direct line of optical wireless transfer function into PR, because as we know, I is equal to responsivity into P power. So this is what I have assumed here. So this becomes sort of I square. So this is the signal power, and this is the noise, the total noise. That noise can come from some natural sources, for example, or artificial light, other than the light which you're using for communication, artificial light. And the receiver also will generate some sort of noise, which we had studied earlier, thermal noise or short noise. So this is the expression for SNR electrical. Now let us try to calculate the channel impulse response. Channel impulse response of the indoor channel. So if you consider the last diagram which I had drawn here, so I have written a generic expression for line of sight channel impulse response, which is actually Dirac delta function coming from line of sight. So I'm referring to this diagram, and I have written the generic expression for impulse response considering Ti as the transmitter and Rj as the receiver. So this is given by this HS0, the channel impulse response, because of the LOS coming from Ti and received by Rj. V is a visibility factor, because sometimes what happens, there may be a blockage between the transmitter and receiver for LOS path. So this will not give any contribution to the receiver. So this could be either 0 or 1 depending on whether blockage is there or not there. So this is called as visibility factor. So this V can be either 0 or 1. ARJ is the total collection area in the receiver of the jth receiver, and cos m phi ij is the radiation pattern of the source, of the Ti source, and Ts theta ij and theta ij, gi theta ij are the optical gain, optical filter gain, and concentrator gain for the transmitter and the receiver. I have used Ij here because there may be many transmitters and there can be many receivers. So that is a generic expression into cos theta Ij. And this rectangular function actually basically tells you that this is how it is defined. It is 1 when the absolute value of x is less than or equal to 1, and 0 when x is greater than 1. So if theta ij is greater than theta c, this theta ij is less than or equal to theta c, then it gives a contribution here. And if theta ij is greater than theta c, then there is no contribution. It is 0. So this condition, whatever I have described here, is mathematically represented as this rectangular function of theta ij and theta c into, say, Dirac delta function. This is Dirac delta function. So this delta is T minus Dij. Dij is the distance between the transmitter Ti and receiver J divided by the velocity of light. So this is the channel impulse response for the line of sight for one Ti and one Rj. Now we need to calculate channel impulse response from non-line of sight component. And non-line of sight component, there will be many bounces. So the light can come to the receiver after 1 reflection or 2 reflections or 3 reflections. So this number can go to very high value, and normally k is tending to infinity. So we need to understand or calculate the channel impulse response for k bounds, which I represent as this HSK T from transmitter Ti and Rj. And to understand this, how do you calculate channel response of when the light has suffered k reflections? So let us just try to understand this. This is a typical, say, room. So for the simplicity, I have kept the transmitter here, receiver here. This is T. This is T, this is say R, or let me write Rj, this is Ti, and there is some area I consider here, which I called as sigma, the differential area I called as this area, let me call as sigma T. See, the light from Ti strikes the wall, gets reflected, and reaches say here. Now this becomes a transmitter for this receiver. So light will fall onto this receiver. So I have shown here only one reflection, but I'm trying to calculate the CIR for a K bounce. So I have to calculate what is the channel response because of one reflection. Then I'll calculate based using this one for the second one, and using this second for the third one. And for finding out the kth, I need to find out the K minus 1 reflection coefficient, and then if you convolve with K minus 1 channel impulse response with this impulse response shown here, then you get the channel impulse response after K reflections. So this is what it's written here. So this will be, if you see here, this is HS 0, this is direct line of sight, and this is function of T, and this is coming from, this is now acting as a transmitter, so this is D sigma T, and this is Rj. Whereas if you see here, this is as of the kth minus 1, because I'm trying to find out the channel impulse response for K bounce. So this is a HS K minus 1 T, and this will be coming from the transmitter Ti, and this is some small area D epsilon R. So I need to convolve this channel impulse response with this channel impulse response. I will get the channel impulse response for K bounce, which is what is written here. So this is by mistake, this is not there. So this is integrated over S. This is the channel coefficient, reflection coefficient, and then this is the area D epsilon R here. HSK minus 1, this is what is written here, in convolved with this HS0 for the direct line of sight when there is a differential area which now acts as a transmitter for this receiver, is given by HS0 D epsilon T into Rj. So if you take the norm of this, that is the norm of this for high value when K is tending to infinity, because every time the ray is striking the wall, because the reflection coefficient is less than 1, it is getting attenuated. So when it does for very high amount of time, or for a high number of times, then this value tends to 0 as K is tending to infinity, because your reflection coefficient rho is less than 1 everywhere. So the overall CIR, if I want to calculate, then it will be sum of all the reflections, all the K reflections. This here in this expression, for example, K is equal to 0 is a line of sight, and K is equal to 1 to infinity is non-line of sight. And as I mentioned, that as K tends to infinity, this value, this contribution from high values of k will tend to 0, and effectively you can write this as equivalent to summation k is equal to 0 to n, where n is some number which has significant contribution to the channel impulse response, hsk t of ti and rj. And it has been seen experimentally or using some software tool that this n value actually is between 3 and 10. After that, if you have n value more than 10, it has very, very low impact on the channel impulse response. So for all simulation or practical purposes, the n can be between 3 and 10. So this is channel impulse response of for a system which has only one transmitter and one receiver. So we have considered both a line of sight as well as a non-line of sight. And we have seen that channel impulse response is basically combination of channel impulse response, the line of sight, plus the reflected components, where this number of reflections which can be considered can be between 3 and 10 to give you an accurate value of channel impulse response.